Today's honors geometry lesson is on section 5.5, Theorems for Similar Triangles. Our objective is to state and apply the side-angle side and side-side-side theorems for similarity. The side-angle side theorem of similarity states if two sides of one triangle are in proportion to two sides of another triangle and the included angles are congruent, then the triangles are similar. The side-side-side theorem for similarity states if the sides of two triangles are in proportion, then the triangles are similar. So let's take a look at a couple examples using our angle-angle, which we learned in the last lesson, our side-angle-side, and our side-side-side theorems for similarity. The most important thing for this section is to make sure you draw and properly label your diagrams. So example 1 states, suppose AB equals 5, BC equals 1, XY equals 15, YZ equals 3, and angle A is congruent to angle X, can we prove that triangle ABC is similar to triangle XYZ? So let's start by drawing triangle ABC and labeling AB 5 and BC 1. Let's label our second triangle, which is XYZ. We know that XY is 15 and that YZ is 3. The other information that they've given us is that angle A is going to be congruent to angle X. Okay, so based on the markings, we can see that this is not going to meet the criteria for angle-angle because I only know one angle, and it's also not going to meet the criteria for side-side-side because I'm missing the third side. So the last thing we're going to want to check is they've given us an angle and they've given us two sides. As you can see, angle A and angle X are not included with the side lengths that are given. So based on the information, no, we cannot prove these triangles similar, and therefore we don't have a theorem to support proving these triangles similar. So for B, we're going to suppose now that, so draw a triangle, so ABC. We're going to assume that AB is 5, that BC is 1, and then in our second triangle for XYZ, XY is 15, and YZ is 3. But this time they told us that angle B is congruent to angle Y. So again, we only have enough information to possibly prove side angle side. So angle B and angle Y are included. So it is going to be an example of side angle side if the sides are also in proportion. So if you look at side AB to side XY, that has a ratio of 5 to 15, which is a scale factor of 1 to 3. If you look at the second sides that were given, side BC and side YZ, you're going to see that BC has a side length of 1 and YZ has a side length of 3. So again, that scale factor is also 1 to 3. So therefore, we have two sides that are in proportion, an included angle, and another two sides that are in proportion. So we can prove that triangle ABC is similar to triangle XYZ based on our side angle side theorem. In the next example, we're going to suppose that AB is 24, BC is 8, and that AC is 20. And for the second triangle, for XYZ, we are going to assume that XY is 18, YZ is 6, and XZ is 15. Because we've been given three sides in one triangle and three sides in a second triangle, the only thing we could possibly prove would be side, side, side. In order for that to work, we have to prove that all three sides in the first triangle have the same proportion or same ratio as those in the second. So when you do this, you want to match up sides. You want to match up the smallest side in triangle ABC to the smallest side in triangle XYZ. So in ABC, 8 is your smallest side. In XYZ, 6 is your smallest side. Then we're going to match up the two sides that are in the middle. So the second smallest side. For ABC, that's going to be side AC, which is 20. And in XYZ, that is going to be side XZ, which is 15. And now we're going to match up the largest side in each triangle. So the largest side in triangle ABC is 24, and the largest side in triangle XYZ is 18. So if these all reduce to the same ratio, then we would say that all three sides of ABC are in proportion to all three sides of XYZ. So 8 over 4, 20 over 15, and 24 over 18 all reduce to 4 over 3. So therefore, we can say, yes, these triangles are similar based on side, side, side. This time we're going to suppose that in triangle ABC, so A, B, C, that angle A is 20 degrees, angle B is 20 degrees, which means if we complete the triangle that has to equal 180 degrees, we now know that angle C is going to be 140 degrees. In the second triangle for XYZ, we are to assume that angle X is 15 degrees, angle Y is 15 degrees. Therefore, if we complete the triangle, we know that angle Z is 150 degrees. Because we have not been given any of the sides, the only postulate or theorem we could look at would be angle-angle. And in order for that to work, we have to have at least two angles of one triangle congruent to two angles of the second triangle. And as you can tell, we do not have that scenario. So we would say that we cannot prove these triangles similar. Therefore, we don't have a postulate or theorem to support that. And lastly, we're going to look at the last example for triangle ABC and XYZ. We have A, B, C. And then on this one, I'm going to go ahead and draw the second triangle of X, Y, Z. So for this one, they didn't give us actual angle measures, but what they've given us is that angle A is congruent to angle B, which is congruent to angle X, which is congruent to angle Y. So since AB also equal XY, we do have the angle-angle similarity postulate, and therefore we can prove these two triangles are similar. For the next couple examples, we are going to try to prove the triangles are similar, and if they are, we're going to state the similarity and then tell which similarity theorem or postulate we used. This section, it's very important to remember that if you have triangles that are confusing when they are one figure, go ahead and separate them into two figures. So I'm going to take the first triangle, which is ABC, so A, B, C, and I'm going to label the information that I know. I know that AC has a length of 12 and that BC has a length of 9. And for the second triangle, move this over here, we're going to go ahead and label that. This is E, D, C. I know that EC has a length of 8, ED has a length of 6, and I do not know the length of DC. What I do know is that in triangle ABC, angle C is 20 degrees, and in triangle CDE, angle E is 20 degrees. So the first thing we need to do is to see if these triangles are similar. So based on the angles and the side measures that they've given us, we can possibly prove side, angle, side. So we do have an included angle that is the same for each at 20 degrees. What I need to do now is I need to prove if the two sides that have been given to us have the same ratio. So again, remember to match up the smaller side in ABC to the smaller side in CDE, and so on and so forth. So for triangle ABC, the smallest side given to me is 9, and in triangle CDE, the smallest side given to me is 6, so those two are going to be matched up. In triangle ABC, the larger side given to me is 12, and in triangle CDE, the larger side is 8. So if we look at 9/6 and 12/8, we can see that they both have the same scale factor of 3:2, and therefore this triangle is proportional. It is going to be similar. So we now know based on the markings that we have side, angle, side, and that triangle ABC is going to be similar to triangle CDE. Okay, For the second example, so for example B, there's really no need to redraw the triangles, but what we do need to do is to complete the triangle. So we know that 54 and 64 is going to leave angle B here at 62 degrees, and that angle 62 and 64 is going to leave this angle here at 54 degrees. So we can see that there are at least two angles in ABC that are congruent to at least two angles in CDE. So we can now say, based on angle, that triangle ABC is going to be similar to triangle CED. For example C, we have been given two sides in triangle ABC and two sides in triangle CDE. The only other information we can conclude is what we know about vertical angles. So we know that angle BCA is going to be equal to angle ECD. So based on the markings, we're given one angle and two sides. Since the angle is not included between the two sides that have been given in each triangle, there is no way to prove if these triangles are similar. So since we can't prove that these are similar, we cannot complete our similarity statement. For example D, it's going to be very helpful to go ahead and separate the two triangles. So as we did in the first example, in example A, we're going to go ahead and redraw each triangle. This is triangle A, B, C, and I'm going to label the side length. So AB is actually going to be a length of 10, BC is going to be a length of 8, and AC is going to be a length of 12. And I'm going to go ahead and do the same thing for the smaller triangle. I'm going to relabel. So this is D, this angle is B, and this angle is E. And from the diagram, I know that this has a length of 4, 5, and a length of 6. So based on the given information, I've been given all three sides of ABC and all three sides of DBE. So I'm going to try to prove that all three sides are in proportion. So again, remember to match up the smallest side in ABC to the smallest side in DBE. So ABC has the smallest side of 8, and DBE has the smallest side of 4. Now I'm going to match up the middle side. So in triangle ABC, AB is going to be the middle side, and in triangle DBE, 5 is going to be that middle side. And then lastly, I'm going to match up the largest side in each triangle. So the largest side in triangle ABC is AC, which is 12, and the largest side in triangle DBE is 6. So if we take 8/4, 10/5, and 12/6, they are all simplified to the ratio of 2 to 1. So therefore, we can say that all three sides are in proportion based on side, side, side. And we now know that triangle ABC is similar to triangle EBD. For our last example, we're going to use the chart below, and we're going to determine whether a triangle with vertices ABC can be similar to a triangle with vertices DEF. And if we can prove that they are similar, we're going to state the similarity and the scale factor. So again, it's very important for the first example to draw each triangle and label. So we have triangle A, triangle B, or triangle ABC, sorry. And then in the second one, we're going to have triangle DEF. And now we're going to use this for our first example to see if we can prove them similar. So AB has a length of 8, BC has a length of 4, AC has a length of 6, and then DE has a length of 2, EF has a length of 4, and DF has a length of 3. So based on the given information, we're going to try to prove side, side, side. And remember, you need to match up the sides in each triangle correctly. So in triangle ABC, the smallest side has a length of 4. In triangle DEF, the smallest side has a length of 2. In triangle ABC, the middle side has a length of 6. In triangle DEF, the middle side has a length of 3. In triangle ABC, the longest side has a length of 8, and in DEF, the longest side has a length of 4. So if we take 4 halves, 6/3, and 8/4, we can see that they reduce to a scale factor or ratio of 2 to 1. So we know that our scale factor from ABC to DEF is 2 to 1. And now we know that triangle ABC is going to be similar to triangle FED. For the second example, we're going to again use triangles ABC and triangle DEF. So for the second example, we know that AB is 12, BC is 18, AC is also 12, and then in the second triangle, we know that DE is 16, EF is 16, and DF is 22. Okay, so again, I cannot stress how important it is to make sure you match up the appropriate sides. So in triangle ABC, AB and AC have the same side length, and in triangle DEF, DE and EF have the same side length. So those are going to be considered the smallest and the middle length. So when we match those up, we can say that AB is going to be, hopefully, if we can prove it, proportional to DE, and that AC, which is 12, could possibly be proportional to EF, which is 16. In triangle ABC, BC is our largest side with a length of 18, and in triangle DEF, our longest side is 22. So if we start to reduce, we're going to see that 16 gives me 3/4, and again 12/16 gives me 3/4, but 18/22 gives me 9/11. Which means that only 2 of the sides are in proportion and not the third side. So therefore, we cannot prove these two triangles similar, so therefore there's no similar statement. And since there's no similar statement, or they're not similar at all, then there is no scale factor. So this concludes the lesson on 5.5. If you have any questions, watch the video for a second time. And if you still have questions, write down any clarification questions that you may have and bring them to the next class.